Good day, everyone. My name is David Gigagne. I am a senior engineer with ITASCA Minneapolis, responsible for technical marketing. Welcome to our webinar today, introducing IMAT, ITASCA's Mining Analysis Toolbox. Today's presenter is Gys Basson. He's a numerical modeler, software engineer, and seismologist with ITASCA Australia. He has over 15 years of experience in the research and development of computational tools for rock mass behavior in deep, hard rock underground mines. He has implemented several numerical solvers involving the boundary element method, finite element method, discrete element method, materials point method, and successfully used these tools to address a wide range of real 3D mining-related research projects.
Good morning, everyone. Thanks, Dave, for the introduction. So I'll start this this webinar with just 5 quick slides and describe to each of you what IMAT is, now integrated flag 3D, and how we try to make a simple user interface to the flag 3D software. So the first slide, just if anyone has any questions, or please feel free to click on the Q&A button, and any questions will be answered at the end of this webinar. So what's IMAT? IMAT is powered by flag 3D. So we have visited several mines over many years, and we have heard concerns that some of the software might be slightly complicated. So what we've done is we've added a brand new user interface on top of flag 3D. This user interface is a standalone interface. It doesn't require flag 3D, but it integrates with flag 3D when you are solving models. So IMAT is a pre-processor and a post-processor to flag 3D. The idea is we provide mines with a very simple user interface. The main design of IMAT is to be extremely simple and save miners time. So it's a point-and-click interface. There's no scripting required, and all settings and configurations are done via this point-and-click interface. It's got quite powerful features. It relies on flag 3D for solving, and as many of you that use flag 3D in the past know, that it's a powerful solver, but we've developed some really powerful pre-processing and post-processing tools to rapidly build numerical models fast. So the example that I'm going to be showing you today in real time will use a real mine case with 10 mining sequences, and we are going to see within the hour if we are able to build and do some post-processing with this model. And for those of you that are interested, there are several options available to IMAT. It's a plugin-based system. So one way that we actually keep the software simple is that you don't have to opt in for every single feature of IMAT. You can only opt in for certain features that you want. So for those of you that, for example, want to do seismic analysis or view seismic data, you can use only the seismic plugins, or if you want to use IMAT for pure numerical modeling, you do not have to choose the seismic analysis plugin, for example. I'll be showing more of this in a minute. So I'll just end that there, and we'll start IMAT. And when you first install IMAT, you will be welcomed with a screen that looks like this. Hi, and welcome to IMAT. And here you could choose whether you want to use a light or dark theme. Many users choose the dark theme, and many night owls like the dark theme. Personally, I like the light theme, so I'll go ahead and use the light theme for this presentation. You've got several options. If you have an IMAT license, you can create a new project from scratch, or you can open any of your existing projects and just continue working from those. I'd like to, before I start a new project, I'd just like to add this caveat. All the data that I'll be showing you today are from various mines. It is not mine specific. The stress tests that will be used to build and solve numerical models is all fabricated. as well as the seismic data. So this data doesn't belong to one specific mine. Furthermore, IMAT doesn't have a PDF help manual or an online help manual. During our visits to several mines, we've realized that miners do not have time to read manuals or read long documentations. So what we've done is we've created an IMAT help system by the means of how-to videos. And the first how-to video can be accessed right here, how to create an IMAT project. This will launch your web browser, point you to our YouTube page, and it will automatically load that video on how to create an IMAT project. So let's get started. I'm going to create an IMAT project from scratch, a brand new one. I'm going to be importing some geometries, and I'm going to build a model and attempt to solve it, as well as do some post-processing and doing some contours. So let's get started. I'm going to create a new project. We specify the project name, so I'll just call this the ITASCA webinar project, AM version. We need to specify project location. Where will this project be stored on our hard drive? We can specify a mine name, and the mine name is typically used in things like videos and screenshots that IMAT creates. IMAT is designed around the concept of time. So time is a very important aspect of IMAT. So it is important to get, for example, the time zone in which your mine operates correctly. We need to specify the mine's reference system. In this case, the mine's x-coordinate increases in east, y in north, and z in upwards, and then distance units. For our imperial users, you can choose between meters and feet. And then I'm not going to spend too much time on what the reference coordinate is. The reference coordinate is just an IMAT automatically. If you have a mine that operates in a very large coordinate system, you can choose a coordinate at the center of your mine, and IMAT will automatically move all geometries from that coordinate system, so that 3D rendering, for example, occurs faster, and model building and solving will be more optimized. And for this example, I'll just leave the reference system as is. So I've just created a new IMAT project. This is the user interface. On the left, we've got the project explorer. All items highlighted in black are what we call modules or plugins to IMAT. All the bold items. And a point that I made earlier, if, for example, you only choose to use the flat 3D modeling plugins and not, for example, seismic data or charts plugin, your license will govern what the user interface looks like. So if your license only allows for the modeling part, you'll only see this in your user interface. And that's how we try to make the interface as simple as possible for user. We've got many features in the IMAT, but the key to this interface is simplicity and speed. We want to do things fast. So I'll just go ahead, and I'm just going to turn back on all plugins. There's one item that's not highlighted in bold. This is the project settings. These are global project settings. And if I expand it, there are various global project settings that you can set. For example, your mine's in situ stress state, or its local magnitude scale, and the reference coordinate that I referred to earlier. Also, I mentioned earlier on the point that IMAT does not have a help manual, but all help, we try to give as much information as possible through the information window about that specific item. So if there's something that you can click on, for example, this is our geometries plugin, where you can basically just import some geometries and all the kinds of formats that we support. We try to show that via this help, via the info window. Furthermore, I mentioned we use videos, how-to videos, to show how some of these features work. For example, the block models plugin, there's a how-to video that points you to a YouTube video where you can see how to import and visualize block models. So IMAT's scattered with many of these how-to videos for each of these plugins throughout the user interface. So let's get started. The mine a mine has provided me with some data, some geometries. They've given me the block model data. They give me their geometry data, cave, lithologies, rings, stopes, etc. They provided stress state and then as well as seismic data, and we are going to use this information, visualize all this information, and then build the numerical models. So we are going to take the mine's geometries and we are going to import them using the geometries plugin. And the first step we're going to do is simply just visualize them. So I'll expand the geometries plugin. There's some information for those users that want to read on which formats we support. You'll see by default we've created 3 separate folders for these geometries. So to import data into IMAT is simply a right-click import option. You can point to the files that you want to import. For those of you that want to save time, all you have to do is just select the folders that you want to import and drag and drop it onto the geometries plugin. And that will import all the data for you. So you'll see, for example, I've imported tunnels, caves, several lithologies, rings, solids, and so forth. You can simply turn on any of these geometries by clicking the I button next to that specific geometry, and the 3D viewer will render that information that's currently visible. I'll also turn on, for example, my rings. And these are all the rings that were provided to us. And for this example, I'm not going to turn on all the cave shapes. I'll just have one particular cave shape that I'm going to show here. Just turn that off again. And what I'll do is I'm just going to change the colors on all my ring shapes, so it would make visualization easier. So I'll right click, I'll randomize the colors for all these rings, and that looks a little bit better. So I've just quickly and easily imported geometries that I potentially want to use for my numerical model. Next, I'm going to import a block model that the mine provided, and I want to visualize this block model data and potentially use it in my flat 3D model. So I'm going to use the block models plugin. Before I import the block model data, I'm just going to show you a file, a typical CSV file that mine uses, and I'll show you how to import that. So I'll go to my block model folder, and I've got a CSV file of this block model. The file is fairly large in this case, well, only 85 gigabytes, but this can be several gigabytes of data. For this particular block model, I've got an XYZ coordinate, and this block model has got a Young's modulus, Poisson ratio, density, UCS, GSR, and MI assigned. And I may choose to import all of these columns or simply just pick and choose which ones I do want to import. So just to make my life easier to see in which columns all the information is located, I'm just going to do this. So I can see that XYZ is columns are in columns 1, 2, and 3, Young's modulus in column 4, and etc. So let's say I'm going to import for this particular block model density, maybe UCS and GSI. So I want to import columns 4, 7, and 8. So to do that from the CSV file, I'll right click, import a block model, select the file. And then I need to specify in which columns the information is that I want to import. And I just want to pause there for a second. So IMAT has got generic CSV importers. If you've got data in CSV files, most of the importers in IMAT is based around this generic importer. You've got to specify some name, and you need to specify in which columns to find that information. So for this particular block model, let's call it my IMAT block model, because I'm going to use this block model to change some of my IMAT properties. I'm going to regularize this block model with a 25 by 25 by 25 meter grid. I specify that the x column, the x coordinate is located in column 1, y and z in column 2 and 3. Young's modulus was in column 4, if I remember correctly. So yeah, Young's modulus 4, UCS and GSI 7 and 8. So because I want to use this for an IMAT constitutive model, I'm going to use IMAT UCS, column 7, and I will import an IMAT GSI, column 8. Just give that a second to import. So I've just imported that data, and now I can, firstly, before I use it in my numerical model, visualize a block model. So there's my IMAT block model. There's a grid that was provided in that block model, and here are columns that's available: Young's modulus, UCS, and GSI. What I might do is visualize GSI, but it works the same for any of the other parameters, and there are 3 options to visualize these parameters. The first way is using a classical cut plane option. You can use a cut plane, and you can scroll through your data simply by using a cut plane. So for those of you that's used flat 3D before, this is very similar to the cut plane that exists in the flat 3D interface. And this cut plane doesn't have to be vertical. You can change the orientation in any way you like. Secondly, you can view the information in terms of isosurfaces. So these isosurfaces are probably not the cleanest isosurfaces in the world because the data varies quite a bit. But if your data is mostly uniform, you'll get nice isosurfaces. Probably the most valuable way to look at block model data is to interpolate it onto a wireframe. So what I'm going to do just for the block model visualization is to interpolate that data onto a wireframe. And to show that, I will use the cave shape, my final cave shape. So what I'm showing here is the final cave shape and GSI interpolates onto that shape. Another instance where this might be extremely useful if you want to interpolate material properties onto a pit shell, for example, or maybe onto a structure, for example. So this is how you can use the block model plugin to import the block models and visualize. Later on, during this presentation, I'll be showing you how we can override or use these block model properties in our flat 3D model. So I'm going to go ahead and I'm going to start setting up a flat 3D model, and I'm going to try and build a flat 3D model in 15 minutes or less. So for that, I'll use the flat 3D advanced plugin. And what I'll do is I'm going to create a new flat 3D project, and I'll call this project 1. You are not limited to one project. You can create as many as you like. So say, for example, you are doing a calibration project where you want to vary maybe the in-situ stress states or vary several material properties. You can create as many flat 3D projects as you like. So I've just created this project, and the project is set up in the order, in the workflow that we at ITASCA follow when we do a numerical modeling project for our clients. So there's a project setup phase, there's the pre-processing phase, there's the model phase or the solving phase where we actually get flat 3D to solve our model, and then there's the post-processing phase. We are going to work through all of this in sequence and build a model and then get it to the point where we solve it in flat 3D. So the first thing that we usually do is set up our in-situ stress. The in-situ stress information that the mine provides us, we enter that information in this item using the properties window. So we need to specify a mine's datum. That's usually the free surface level. And for this particular case, I will just set it to 1000. I need to choose whether or not I want to use gravity in my model. Does the stress vary with depth? And in that case, we need to include gravity in our model. And then we need to add components of the stress tensor. So I'm just going to go ahead. I'll specify just random values for this example for the stress state for this one. So I can specify a fixed component of 10 MPa for sigma 1, maybe 5 MPa for sigma 2, and 1 MPa for sigma 3. And then a stress component varying per meter, MPa per meter as depth increases. So we can go ahead, 10.03, for example, 5. That's the magnitude of our stresses, and we need to then also specify the directions of our principal stresses. So for this mine, I will have a sigma 1 with azimuth at 150 degrees. I can maybe allow it to plunge 10 degrees. You'll notice if I enter a non-zero sigma 1 plunge, I do not have to enter the sigma 3 plunge. This is because we can calculate all the other directions automatically to ensure orthogonality of the principal stresses. So I'll add a plunge to my sigma 1, and then I can add maybe another azimuth for sigma 3. So I've just configured my stress state. The next step is to configure the boundary conditions that we use in our model. So typically, for most of these mine scale models, flat 3D is a domain-based method, and we need to choose the type of boundary condition that we want to apply to our domain. We've got the options between free, fixed, roller boundary conditions, or stress boundary conditions. For this example, by default, we will keep everything fixed. But if, for example, I had a free surface or maybe a pit shell, I will make the upper Z boundary free. This mine, I'm not going to model all the way to the surface, so I will keep the upper Z boundary fixed. The next step is to specify our mining sequence. So for this particular mine, that provided us with close to 100 mining steps for this sequence. I'm going to import 10 of those, and I will be building a model using 10 mining steps. So to specify that mining sequence, we right-click and create new steps. We will start at step 1, and we will have 10 steps. I mentioned earlier on that the concept of time in IMAT is extremely important. So we need to specify that our first steps start in maybe January 2010. And it says 1st of January 2010. And each step represents either a daily, monthly, quarterly, or yearly step in the sequence. So for this example, I'll use a monthly step. So IMAT just created those 10 steps in the mining sequence. You'll notice, compared to the other items in the tree, that the text is highlighted in red. This is to show the user that we have a mining sequence of 10 steps, but we haven't solved the model yet. It's just a visual indication that the models haven't been solved yet. If you expand any one of these steps, we need to specify, import our pit shells, tunnels, stopes, rings, cave, and cave geometries. If we have those, you do not have to use all of these items, but this is where you would import your geometries. You can do it one by one. I showed earlier on drag and drop features. You can do it one by one, but that is extremely time consuming, especially if our survey department at the mine provided us with potentially 1,000 different files. So if your files is named in a way that IMAT can interpret it, and I'll show you some examples for my geometries. Let's say, for example, I've got cave geometries. I've got a file name. This can be, in this example, it's an STL file, but it can be DXF or SURPAC or any format. If it's got the step number in the file name, IMAT will know how to automatically import it. So I'll go ahead. So I've got all of these step numbers already assigned to my cave geometries, rings geometries, slope geometries, and tunnel geometries. So you can auto import them. And it's quite simple. You just right click, import, auto assign geometries from folders. I will select those folders. I've got caves, rings, slopes, and tunnels. These will represent my mining steps. And open. And IMAT will open up an output window here in the bottom corner, and it will display whether or not it was able to correctly associate each file with the correct mining step. In this case, everything imported successfully. So I'm going to turn off my block models and my geometries, and I can click on this icon here to visualize my mining sequence. So all the geometries imported correctly. There's 2 steps left in building in our workflow for building a model. Is we want to specify a model domain. Remember, flat 3D is domain-based method, so we need to specify the extent of our domain. And then IMAT relies on octree style measures. So we will specify a domain, and we will specify areas where we want refinement in our mesh to improve accuracy in our numerical model. So I'll turn on my model domain, and as you can see here, it's not covering my mining excavations. So I need to move it and potentially scale it. It's quite easy. You can click on any one of these coordinates to manually enter them, or just click on that and say, I want my domain centered around that point. So my box moved. Now, this domain is still relatively small. Typical rule of thumb is that the domain extent needs to be at least 5 to 8 times larger than the dimensions of our excavations. So I'm going to scale this, and there's a few ways you can do it. You can either manually specify the domain extent, or you can use the control buttons to move. So I am currently scaling it in that direction of the red arrows by simply rolling my mouse wheel. And I will translate it maybe slightly upwards, and I will also scale it in the Z direction. Okay. This domain might still be relatively small. We probably want to make the boundary slightly larger, but for this example, I think this will be sufficient. So on my model domain, for my octree grid, I need to specify my largest zone size. And from there onwards, we're going to continually refine the model to areas where we want small zones. And this will typically be close to the tunnel. So I'll start off with the 20-meter zone sizes. Then on my domain, I will add a new refinement. And I will call this refinement my tunnels refinement, or my development refinement. I'm going to specify that all zones within a specific distance from my development needs to be refined down to a certain level. There are other kinds of rules that we can specify refinement as well. We can, for example, specify that if you've got a mine with a layered media and you want refinement in above a specific elevation, you can use that. This rule, for example, will allow you to do refinement above a specific Z level. And there are several others. For this particular case, I'm going to use the distance from geometry refinement. So I've just added my first refinement, and there's my tunnels refinement. Remember, we started with 20-meter zone sizes, and we might want to go down all the way to 2.5 or even 1.25 sizes close to our tunnel. So for this particular example, I'm going to say I want 3 levels of refinement down to 2.5 meter zones. Any zone that locates within 20 meters from my tunnels, and I will select any one of the geometries that I imported, and these are my tunnels geometry. So I've just set up this first rule for refinement close to my tunnels. I'm not necessarily going to refine close to my caves. I can add as many of these refinements as I like. So if I had structures, for example, and I want to simulate ubiquitous joints or interfaces, I can specify another refinement. This again, I will again use the distance from geometry rule and say all zones may be within 20 meters from my structure that I'm going to select needs to be refined down to 10 meters or 5 meters. Okay, so I've specified my model domain and areas where I want zones to be refined in my OptiGrid. The final thing that I have to do is I need to specify my material properties and choose which constitutive models to use. And that's the final step in the pre-processing workflow before we can build the model. So if I expand my material domain, the first thing that I need to specify is my host rock material. And when I select it, we can choose what constitutive model I'm going to use. Default is elastic, but if you can choose whether you want to use hook brown, strand softening, or put on null if you want to remove zones maybe above a tree surface, or IMAS. If you select the IMAS option, you can configure all the IMAS properties through the interface. For this example, I've got 3 additional domains. So I've got 3 additional pathologies. Those are these 3 domains. What I'll do is I'm just going to change their colors so we can see them, visualize them better. And for each of these 3 domains, I want to specify different material properties. It's quite easy. You can right-click, add a new refinement. Apologies for that. Right-click, not a refinement, right-click, add new material domain from geometries. I'm going to select those 3 lithologies. We need to specify whether they are planar geometries or volumetric. In this case, as you can see, they are volumetric, so they are called polyhedrons, closed polyhedron geometries, and they get added here automatically for you. Then for each one of these domains, we can go ahead, specify which constitutive model we want to use, change the material properties. I'm not going to change it in this particular example, but you can go ahead and change the properties in each one of them, and even use different constitutive models for each of the domains. This is where we might choose to override some of these material properties with the block model properties that we've imported. So for each one of these domains, there's an option where we can use a block model that we've imported. Earlier on, we imported the IMAS block model, and we can choose that we might want to override the GSI and UCS properties for these domains. And it's quite powerful in extent how many material domains you can include and how complex you can make it. You can have 100 different block models with maybe 100 different material domains, and each one of those can use different block model properties. So it's extremely powerful in the complexity of the model that you can build in this one. Okay, so I've just went through the entire pre-processing setup, and I'm finally ready to build my model and send it to Flag3D for solving. So I'll right-click on my grid or my model, and I'll use the build grid option. This text explains what this process is. It's a 3-step process. First of all, it constructs the OctreeGrid, then it applies the material domain logic. For each zone, it will set those material properties, and finally, for each zone, it will do what we call the mining sequence logic, where it applies the specific mining sequence to the model. You may or may not choose to do all 3 of them simultaneously. For this example, just to save time, I'm going to go ahead and select all of those. So it's loading all those geometries, and it's currently building the model. And while this is busy, I might go ahead and it will take approximately 4 to 5 minutes to build this grid. Oh, actually, it's quite quick. So the algorithms told me that I'm going to have approximately 2.5 million zones and 2.7 million grid nodes. Do I want to continue? For this example, that's more than sufficient. I'll be able to solve the model in using my laptop. I'll say yes. So it's finished constructing the OctreeGrid. Next, it's going to apply the second phase, applying the material domain logic. And then finally, it is going to go through the mining sequence and assign the mining sequence. So it's just finished step 2. Now we just need to finally do the grouping logic, the mining sequence logic. So just bear with me for another 30 seconds. Hopefully this won't take too long, and then we can continue. Let's just finish step 1. And now it's busy with step 2. Remember, we've got 8 steps. It's busy with step 3 now. So give it another few seconds. While this is busy, we've just completed, as I mentioned, the pre-processing phase, setting up and building the model. We're now at the phase where we're about to solve it, about to send it to Flat 3D. And once it's solved, we're going to use these items in the post-processing phase to visualize contours, for example, stress contours, build movies of certain mining parameters for this mining sequence, etc. So we are nearly done with the model. While this is busy, I might just quickly mention some of the other plugins that I won't have time today to show. Is the first one is the Movie Makers plugin. IMAT has got a specific plugin for if you have data, geometries, or seismic data, for example, a time sequence, you can create movies using the Movies Maker plugin. There's several how-to videos available already to show you how to use that. The seismic data plugin I will use slightly later during this presentation, and then there are seismic system plugins to visualize your seismic sensors if you've got those sensor locations, and then there's a spatial plugins where we can create volumes for spatial filtering. So we're nearly done. It's busy with step 9, and we've got one more step to do, then we can visualize the Flat 3D model that's been generated. Actually, while that's I might go ahead and go, while this is busy, import some seismic data. Actually, yeah, it's just finishing. So give it 10 more seconds. It's just saving the grid. Okay. So we've just built a model with 2.5 million zones, applied the mining sequence, applied material properties to our model in 3 minutes and 43 seconds. So before I solve, I first want to inspect the grid, the model that I've generated, to see if my refinements were correct, were my mining sequence correctly specified, and were all my material properties specified. And again, for those of you that used Flat 3D before, that one way that we can do it is by simply turning on a cut plane. So IMAT's now loading the grid, and we can use the cut plane to browse or cut through our Octree model to see where our different levels of refinements are. And purely from visual inspection here, I can see that software or the model is built according to what I wanted. At 20 meters from my tunnel, I'll refine down to 2.5 meter zones, and 20 meters from any of my structure intersections, it was refined down to 10 meters. We can also view those refinements independently. So you can turn those refinements on and look at the zone locations that were refined down to 2.5 meters, and you can render them as pixels. For this example, I'll render them as faces and just visualize those zones or that volume that was refined down to 2.5 meter elements. So I've inspected my refinements, and I'm happy with the Octree grid that was generated. Next, I want to look at my mining sequence. So I had one step for my tunnel. So again, I'll render those as faces. This is the Octree model. You can see the blocky style mesh, the block style mesh. This is the Octree model, those zones that belongs to the tunnels for step 1. And I can do the same for my rings and my stopes. So I'll turn all of those on. and render them as faces as well. So that looks fine. We can do it for my slopes as well, or maybe do it for the caves as well. So I'll turn on my 10 cave shapes, also bring it in as faces, and just from visual inspection, I'm happy with the model that was generated. So I'm now finally ready to solve my model. For those of you that have worked with Flat3D before, but you don't care about the data files, you can simply right-click, Solve Project. This will start up Flat3D in the background, and it will run through the entire mining sequence, and it will solve it for you. For our advanced users, you can generate a solve data file. So we'll build a solve data file for this example. We'll call it solve. And for those existing Flat3D users, this should look familiar. We've got fish functions that save stresses, displacements, loads, model strain, loads, grids, set material properties, and in situ stresses and boundary conditions based on what we configured in IMAT. And you can change or modify this data file as you wish. If you want to add more complexity to your model, do more advanced things in Flat3D, you can go ahead and take any of this code that was automatically generated for you or modified. You can also go into Flat3D, open the data file in there, and run it directly from within Flat3D. So I'll just go ahead and do that. I will open up the data file that IMAT had generated. Apologies, I actually am in the wrong location. And there's my solve data file. And you can modify it or simply run it from within Flat3D. So you've got flexibility. For users that aren't used to scripting or coding, you can simply, from within IMAT, right-click and solve, and the model will be solved for you. For our really advanced users, you can take this data file, bring it into Flat3D, and modify it as much as you want. Okay, so I've just solved my model, and I want to post-process this model. So in this particular project, I don't have a solved model. Remember, we created one from a clean project. So I'm going to close down this project and open an existing one that was already solved for this particular mining sequence. Go ahead, File, Open Project. And I've got a project that's got a Flat3D project that's already solved. If I expand my mining sequence, remember earlier on, I mentioned that these items in your mining sequence will be highlighted in red. If it hasn't been solved in this example, it has already been solved. So I can now go ahead to the final phase and do post-processing. So the first way that we can post-process the data, again, is by simply using a cut plane. So I'm loading the grid, and I'm going to visualize a cut plane similar to the existing cut plane in Flat3D, and visualize contours, for example, on that cut plane for this mining sequence. Let's just give it a second to load the geometries. So this should look familiar. We talked about the cut plane slide earlier on. So now that I've got solved model, I've got the ability to choose between various modeling parameters that I want to visualize on this cut plane. So for this example, I've got 10 mining steps, and I'm looking at the contours of sigma 1 for mining step 10. You can choose any of the other mining steps that you like and look at contours interpolated onto this cut plane. All of this happens on the fly, so you don't have to calculate it. This is calculated automatically for you. If you can imagine, for example, we've got a mining sequence of 100 or maybe several hundred steps. It will be quite time-consuming to use the cut plane to go to use this geometry. There are other ways that we can post-process the data as well. So let's say, for example, we want to visualize contours of stresses in these pillars. We can use the result points option and add a new geometry. I will move this plane slightly down onto those pillars, and I will simply just digitize the area that I want to inspect. And I can create several kinds of geometries. I don't have time to go through all of them, but for this particular case, I want to create a mesh, and I'm going to contour sigma 1 data, for example, onto this mesh. So I'll call this my pillars geometry. So I've just created a new geometry for this model. Now, you can imagine that stresses and strain data might not, it will not automatically be available. We first need to interpolate results onto this. And to do it, it's quite simple. You just right-click on that new geometry, calculate results, select how many mining steps you want to use, and do the interpolation. And IMAT will load the flat 3D results. It will use that to interpolate stresses, displacements, and plastic strains onto this geometry. It's usually quite fast. You can see in this example, I think for this example, I used a model with 5 million zones. It's using a 5 million zone model, and we, on average, is taking about 4 seconds per step to do that interpolation. So it's almost done. Step 9 and step 10, and saving the results. So now I'm looking at turning on those pillars, and I've got contours of sigma 1 visualized on these excavations for model step 4. We do it for any one of these mining steps now that the data has been interpolated, and we can manually go through the process and visualize these contours. But again, as I mentioned earlier on, it might be extremely time consuming to do this for 100 mining steps, to go through this one by one and manually, for example, creating screenshots to include into a report. And this is where IMAT is quite different from the other softwares, post-processing softwares out there. We try to do the post-processing as quickly as possible. And the way we do it is through movies. So you can use the movies option in IMAT to create a new movie. And this movie, for example, that I'm going to create now for the 10 mining steps will be maybe sigma 1 on my pillars. I want to see the change in sigma 1 on my on these pillars. When creating a movie, we need to specify, do we actually want to visualize the mining sequence in our movies? Do we want to visualize contours? And do we actually want to include seismic data in this movie? And if we do have seismic data that overlaps with our model time range, we can do that, and it will show those seismic data on this movie as well. For this particular example, I haven't imported seismic data yet. I will not use that option. And I need to make a few further modifications to this movie. Again, the item is highlighted in red, showing you that the movie hasn't been built yet. When it's black, the movie is available to play. So the first thing I need to do is specify a movie aspect ratio. The default value is quite good, but if you really want to create high-res movies for presentations or reports, you can really bump this up. I need to specify a camera view. From what angle do I want to visualize my results? And for this example, I'm going to simply just take this plan view, save my camera view. For my contours, I need to specify what geometries, these pillars geometries that I've just created, what modeling parameter I want to use. Do I want to add some transparency? Do I want to change my color scales? There are many different color scales available. Do I want to have a step color map, for example, etc.? There's many options how you can configure this movie. And for your mining sequence, you can also add some transparencies. Sometimes the cave geometries can obscure our view, so we can choose not to move them if we don't want to include them. And then once the movie is configured, just simply right-click and build the movie. This you can imagine if you want to create maybe 100 of these movies, you can set all of them up, start compiling them overnight and tomorrow morning when you wake up, you will have all 100 movies available to you. So in this case, the movie was just finished generating. It's asking me, do you want to play it now? And we'll now go through that movie. And we can see the change. So this is how one way how we can rapidly post-process the results. We've got the ability to create many movies or configure many movies and post-process as many movies as we want simultaneously. So I think for the flat 3D part, I might pause it there for 1 second. I just want to show you the seismic data option. We'll be just importing and visualizing some seismic data. We are running out of time, so I won't be able to show you all the features, but I just want to show you how we can visualize some seismic data. So I'll just delete these existing data sets in this project, and I will create a new seismic data set for my mine data set. IMAT can import several formats. Again, seismic data formats. Again, it's got the classical CSV format, the one that I used during the block model, where you specify in the CSV file where to, for example, find seismic event locations, etc. You can also import the MXWrap EVP format. This is specifically a specific fixed format. So for the MXWrap users that works with MXWrap regularly, you can import that data, or there's an EVP format that I'm going to use to import this for this one. So I've got an EVP file and it's importing one data set. So in this example, I've just imported 216,000 events. There's several things that we can visualize. We can view our seismic data as simply just points in space. We can view it by time ranges. We can several seismic graphs that we want that we can use to visualize this. And again, we can change as with the contours, the modeling contours that I showed previously. There's many different color maps that you may choose to view this information. I'm just going to apply a quick local magnitude data filter just to remove the amount of data that I'm showing here. So I'm going to create a local magnitude filter and maybe look at all events exceeding local magnitude -1. To make that slightly larger, magnitude 0. So these are the events, fabricated events for this mine where exceeding magnitude 0. And I can see the color scale over here. I can, if your mine's got seismic focal mechanisms available for your seismic data, you can turn those on, and we can visualize the focal mechanisms. And for each one of these independently, you can select them, and in the information window, get its information. For example, this event's at this location, this local magnitude. Does it have a source mechanism? Yes or no? If it does have a source mechanism, we can look at the decomposition of the source mechanism. So for me as a seismologist, you can easily see that this was a slip type event. It's got a small isotropic component and large deviatory component. I can look at where it locates on the Hudson diagram, and this confirms that it's close to a double couple or slip type event. And I can even plot the principal axes of this data on a quick steering plot. And you can do that for for any of these events. We can also visualize the principal axes of these events. So remember, the principal axis represents a rough representation of the direction of the in situ principle of the stress at that location at the mine. So you can see what sigma 1 direction is roughly doing for this mine, and the same for sigma 2 and sigma 3. That's sigma 3, for example. Remember, we have a cave here, so sigma 3 is pointing towards the cave. We can also, if for slip type events, we can turn the event nodal planes on, and these are, for those of you that are familiar with nodal planes, know that these are one of two possible structures, planes that slipped for this event. So if we've got known structures in this area, we can compare the nodal planes with that structural data. I think I'm running out of time, we might spend the last 5 minutes for some questions. So I'm going to pause it there. There's many things that I wish I had time for to show you guys today, but I hope that I've given you a good overview of IMAT's capabilities and how rapidly and how easy we can do things, especially on a mine site.
Great. Thank you very much, Gys. So we do have a few questions. The first one is the generated model results on IMAT compatible with FLAC3D?
So IMAT doesn't use a save file for existing FLAC3D users. You know that to save a specific model state, we've got save files. Those the larger the model becomes, the larger those save files can be. So it's nearly impossible for every mining step to have the save file. IMAT saves the data in a different format, and that format is much smaller than a save file, and that's how we are able to rapidly process the data. So if you have an existing FLAC3D model with save files, we need to convert it to an IMAT format, a format that IMAT can read, so we can rapidly process that data.
And then is Python scripting possible once the results have been computed?
So IMAT generates a fish data file, but as I showed previously, where you might choose to just simply take this data file into FLAC3D. There you can, once you've got FLAC3D open with this data file, you can do whatever you like, make whatever modifications you want.
Perfect. Which FLAC3D version is compatible with IMAT?
IMAT needs FLAC3D version 9.1. The data files that IMAT uses to communicate with FLAC3D requires commands that's available in only version 9.1.
Okay. Can IMAT import the same files as FLAC3D? I'm assuming they're referring to geometry files.
If it's geometry files, yes. So if we have a look at the geometries plugin, currently IMAT supports STL, DXF, DWG formats, the SURPAC formats, a few of IMAT's own formats, and then a map3D input file, and very soon, hopefully a VTK file.
Okay. There was a question in the chat about whether or not it can be used with other ITASCA software, and I just mentioned that it's FLAC3D only.
Yeah, that's right.
For setting up the topography instead of elevation, do we have any options?
Yes. So I'll just quickly jump back to where we've got our where we specified our refinement. So on our model domain, there's an option to create a new, sorry, not model domain, over here, a new refinement. Here we can specify the surface level. Apologies, I'm actually in the wrong place. It is a model domain. We'll specify a new material domain, call this my surface, resurface. We will use the above surface topography tool. So if you've got a wireframe, undulating wireframe, even with pit shells or mountain ranges, this rule refers to that. And typically what we'll do is we will select that geometry, point to that geometry, and null the material above the surface topography.
Great. In case of setting up anisotrophies, what options do we have, like shear, fault, etc.?
At this moment, IMAT supports ubiquitous joints, and we are currently working on tools to support explicit interfaces as well. It's not in this version of IMAT yet, but in the near future it will be available.
Great. When did ITASCA develop this tool? How do I convince my consultants to use IMAT? They are reluctant to use new programs due to bugs.
That's a very good question. From my experience as well, I've noticed that it's quite difficult to even to convince my own colleagues to change their workflows. What I can say is that I mean, I hope I've demonstrated this hour-long session that very well tested. We've worked with quite a few mining houses, LKB, BHP, and several other mining houses that did beta testing for us, and we haven't encountered a single bug so far. So I'd like to believe that the software is quite stable.
And did you want to mention sort of how the bug?
Yes, so I mean, in every software, a bug exists. A bug may exist, or and an easy way that you can report a bug to ITASCA is simply by going to the Tools menu, submit a bug or feature request, enter your details, specify whether it's a bug or a feature, or even a question to us. Just give a name, and hopefully in the description field or the body field, give us some detail about the bug. This will log a ticket in our GitHub ticketing system. So there's a formal trace of your bug that's logged. Our developers will automatically get an email with this bug, as well as your application log file. We aim to try and fix the bugs, if it's possible, as quickly as we can, and we will notify you, hopefully within a couple of days, that the bug is fixed. If that's the case, we will also notify you that there's an update to the software available. And you do not have to reinstall the software, uninstall the current version and reinstall it. All you have to do is simply go help, check for updates. The application will tell you that there's updates available with what the specific fixes are that we've implemented, or even new features that we might include in the update. And you simply download it, the application will install it, and you can run it, and you've got the update. So we, again, with the IMAT, we try to rapid support and for mining specific problems.
Will IMAT be extended to model tunneling, including excavation steps and support?
Yes, all of that. So IMAT doesn't currently have the option for support. Again, it's something that we are working on, and hopefully within the next few months, the support option will also be available.
If one does not have FLAC3D, can only IMAT be used for analysis?
If you use the IMAT option with let's say, for example, the seismic data plugins, you don't have the modeling capabilities, you're able to visualize some geometries, but for everything that I've showed today, you do require FLAC3D. It's really strongly recommended to have FLAC3D if you want to do any of or most of the things that I've shown today.
And just to let everybody know, IMAT is when it's bundled with FLAC3D. So when you buy IMAT, you have a FLAC3D license included in that price. So essentially one comes with the other. Then the seismic or IMAS is an optional cost. Okay, we just had a last question. How do you use backfill?
At the moment, through the user interface, there's no option to easily specify which areas you want to include backfill. But if you have a look at the data file that IMAT generates, so I'll just generate one again. There are three functions here that does the extraction for the mining step. There's, for example, one that extracts cave. There's one extract specific mining step. Here you can simply go ahead. Instead of using the zone relax excavate command, you can change the material properties for those zones in maybe the stopes. So you can easily just modify the data file at this point in time.
And we had a question, is IMAT an annual subscription? And the answer is yes. IMAT is an annual subscription. There's a couple options, and there's also academic pricing. And the nice thing about that is as new features, Gys has already hinted at some that are coming down the pipe. If there are new features in IMAT or also in FLAC3D, where we've introduced point releases for FLAC3D. So we're currently on version 9.1, but we have some more exciting point releases coming throughout the year as well to So then you'll always have the latest version and the best technology. Can one use Python with IMAT?
Yes, that's a good question. As I've shown you earlier on, you can IMAT generates these data files. So for the advanced FLAC3D users, what you can do is you can open FLAC3D and we can load that data file. And then you can make modifications and add Python to that if you like. So I'll go, this is FLAC3D. I'm going to go ahead and open the data file that I've generated. Just bear with me for 1 second. I'll browse to that data file. It was generated. You can open it in FLAC3D, make modifications here, and then obviously add Python and make changes to this model as you like.
Great, thank you. How does the Rhino griddle integration work?
The idea is that most of the griddle functionality makes its way into IMAT and automated. So, for example, I showed you some tools that's already available, that's already been ported from griddle into IMAT to do mesh smoothing, to clean up structures. The idea is that for the everyday person, we should not even have to open griddle. Everything happens in IMAT.
Excellent. And if a person wanted to use a FLAC3D grid as opposed to an Octree mesh?
Yes, that's also possible. So in the FLAC3D plugin, you can right-click on a grid and import an existing FLAC3D grid. That can be a non-conforming mesh, it can be any kind of mesh. When you reach the point where you want to build the grid, all that you have to do is do not reconstruct the object grid. So just apply the material domain logic and the mining sequence logic. So you do, so that's how you can use an existing FLAC3D grid that's built outside of IMAT in IMAT.
And this is along the same lines. Can you import a TET mesh? And are the interfaces face commands automated?
So this version of IMAT doesn't yet support interfaces, but probably within the next month or two, IMAT is going to support those explicit interfaces, and it will be automated, and it will create a hybrid Octree TET style mesh that can be solved. So it's coming. It's not far away.
Great. So we had a comment, great content, and a question, will this session be available as a recording? Yes, it will be. So we will be posting to our YouTube channel in the next day or so, the content, a recording of this presentation. Are you planning on adding functionality for coupling, for example, with mass flow?
That's a good question. The idea with IMAT is, as its name says, it's ITASCA's mining analysis toolbox. All the features that our mining clients find extremely useful will find its way into IMAT. So if there's a particular feature that you use often and you think is useful, please reach out to us and we will consider adding that to IMAT. The list of plugins that's currently available in IMAT, this list that I mentioned earlier on during the presentation, the idea is that this list of plugins will continue growing. And the whole idea is to make your life easier and make things faster for you to do.
Okay. This is a similar question as before, just can more complex meshing structures than Octrees be used to create geometries? Yes. I guess as long as it's a FLAC3D grid.
As long as it's a FLAC3D grid file, yes. Yes.
So I guess anything you can build in Rhino Griddle and export as a FLAC3D grid.
Yes, you can bring that in here.
Will we be implementing DFN into FLAC 3D to interpret seismicity in IMAT?
I think that is probably along the
question of explicit structures, like proper interfaces in IMAT. The answer is yes. It's going to happen quite quick, hopefully. I reckon probably in the next month or two that will find its way into IMAT.
I imagine that you'd be able to import a DFN as geometry, and just like you would, you could apply an octree mesh to that if you have a refinement and ubiquitous joints.
Yes, that should be possible.
And then, as you say, the explicit representation of faults is coming.
Yep.
Can IMAT be used to install structural elements? And if so, can it plot it? I'm a little unclear if that means structural support, ground support, or as we've been saying, explicit structural geology.
Yeah, so our first goal now is to add those interfaces for structures, actually structures in our mind. The next step after that is we're going to add support elements, an easy way for users to add support elements to these models.
Right. Do you require a license to view the results?
That is a very good question. We actually talked about that today. At this point in time, yes, you do require a license, but there may be an option in future where you don't have the building and solving availability. You can do you can only post-process models, for example, that's done by consultants like ITASCA. So we will send you those results, send you the IMAT project, and you can use IMAT to post-process and visualize the results.
Can you export the result files for visualization in a third-party application?
Yes, you can. So I'll just demonstrate how that's possible. On your FLAC 3D grid, you can right-click Export Model Results. You can select your mining steps that you want to export. Just bear with me, I'm not going to apply an offset. You can choose which modeling parameters you want to add to those files. And I'm not going to do this now. It's going to be quite large data. I've selected quite a bit, but this will automatically create a CSV file that you can use in third-party softwares like ParaView, for example.
Excellent. Oh, and then we just had a question of a person who was interested in a trial version. And yes, so if you're interested in trial version, please just send an email to sales@itascasoftware.com and we can help you. If you ask for a trial via the meeting chat, then I'll contact you directly. All right. Are there any other questions or comments? Excellent. Well, thank you, Gys.
Great. Thanks, everyone. Thanks for attending. Yeah, well, hopefully speak to you again soon.
All right.
Great. Thanks.
Thank you, everyone. Take care.
Take care. Bye-bye.
Bye-bye.